I will give a talk in front of distinguished scholar in dengue, Professor Scott Halstead, whose earlier paper, I believe it was 1968 papers with Diane Fisher, inspired me all along until now, so that I am still interested in modeling dengue incidence and dengue transmission. And of course, Bob Shope, who in 1992 advised me to look into climate change, and I, as a student, until now I'm also interested in climate change, and the president of the university appointed me to be the director of a Center for Environmental Studies here at Gajah Mada University. And it's disheartening, in fact it's a sober look if we, of the exponential increase worldwide in the incidence of dengue, reported dengue cases to WHO. I think it's very famous graph from WHO guidelines 2009, page 4, and seems that dengue epidemiology is very complicated, and people even predict that it's maybe fourfold or eightfold than those reported here. And one of the most highly cited paper by Simon Hills at Lancet 2002 showed that there would be an expansion of transmission of dengue, the probability of transmission of dengue, including much of southern United States and Africa, Northern Africa, which previously didn't experience any transmission of dengue virus. This is an old map, an old graph by Dr. Kubler, showing that over the years there's an increase in circulating serotypes. It's interesting that the first 4 serotypes already circulating in Indonesia in 1970. So in fact, dengue hemorrhagic fever was reported by Dr. Partana and Partana in Surabaya in 1968. So it's interesting that in 1970, the 4 serotypes already were already circulating in Indonesia, and then of course in 2011 it's everywhere. We understand that until now these are the most common factors implicated in the increasing dengue incidence: the population growth, urbanization, poor solid waste management, unprotected mosquito potential breeding places, complacency about mosquito control, and this is, I think, very relevant today, no entirely effective vector control methods, especially when I listen to presentation from Singapore, because Singapore is a very developed country with high commitment to control dengue. And I saw the map, the GIS, where the ophid trap is everywhere, and actually it's not randomly distributed in Singapore, because in certain places, especially in the south, there are a lot of positive larvae or mosquito traps in the ophid trap. So I think it's interesting that how difficult it is with such resources to control the epidemics of dengue. I think also people always, although it's still unproven maybe, the global travel has been implicated as one factor of the increase in dengue infection worldwide. So now we come to prediction of climate change. And even if if we do everything we can, there would still be an increase in temperature with followed by hydrodynamic changes. But if our current position is still like this in trying to mitigate the climate change, then maybe there will be substantial increase in temperature in 2100. And if we look at research by Dana Fox, published in 1995, that the extrinsic incubation period, the incubation inside dengue vector, will decrease from 12 days in 30 degrees Celsius to 7 days, 5 days decrease in at 32 to 35 degrees Celsius, meaning that only in a short period in the mosquito then dengue will be transmitted to human. So, and then Koopman developed model that decreasing incubation period by 5 days may lead to 3-fold higher transmission rate of dengue. So first, we think that increased temperature, especially from 30 degrees to more or less 35. We are now at this position. Sometimes in Yogyakarta is 32, 33. So maybe in a very few years we will have 3-fold increase, I don't know, of dengue transmission. But it's not as simple as that. And we try to, because it's difficult to model climate change, so we try to understand the effect of temperature on the increase or on the fluctuation of number of cases of dengue. So if we look just at the temperature, does not readily apparent that there's no association. We only use it's just an exercise. We use short-term data, but it's difficult to figure out if there is association between these two graphs. And this is a recent paper by Morin et al. In the Environmental Health Perspectives, that actually, if we look just at temperature increase, then it might cause the survival of adult mosquitoes. It might cause different dynamics in blood fat, and also in extrinsic incubation period. So there are different dynamics, and in fact it might be saying that the higher the temperature, the lower the survival of the mosquitoes. So that's the controversy of modeling of dengue incidence as a function of the change in the temperature. So this recent article then even make things become so confusing, but so it means that we have to use many parameters, these parameters, with more complicated mathematical modeling. And a recent article in PNAS showed that it's not just the increase in temperature, it's also fluctuation or diurnal temperature range. In fact, range. If we have 20 degrees Celsius range, then the survival rates, following infection by dengue virus, then the survival rate of the mosquito will decline very fast compared to if there's no fluctuation of the temperature. Temperature is constant. So we have to consider diurnal temperature range in our model if we want to look in the long run the changes in dengue incidence as a function of climate change. And in fact, we have to look also at the ambient temperature. If it is less than 18 degrees Celsius, then the diurnal temperature range increase might be having a negative influence to transmission, will increase transmission at less than 18 degrees Celsius. However, if the temperature is more than 8 degrees Celsius, then larger diurnal temperature range will reduce dengue virus transmission. Again, this is another variable that we have to take into account in our modeling. However, if we look at rainfalls, it's pretty much predictable with lag. That's why in Simon Hale's paper, he just used one variable, the humidity, which is effective in, according to him, it's quite effective in predicting the incidence of dengue. And if we use both temperature and rainfall, then we know that it's only monthly incidence of dengue from only several years here, and we have quite high sensitivity and specificity to predict the increase in the incidence of the reported dengue cases. Of course, we only have a short span prediction time, only 16 weeks, and if we put more detailed data like weekly reported cases and weekly average of temperature and rainfall, then we will have some increased sensitivity and specificity. So I think it's quite good model with time series Poisson multivariate regression model. And it's not very difficult because there are softwares which could be used to do this kind of, exactly this kind of modeling. And for early warning system of dengue outbreak, I think it's quite useful to do this kind of analysis. So we will know that in 16 days, well, it's not very long from the time the problem is that if we have a lack also in the collection of data, then the prediction would be useless because outbreak already occurred, and then we cannot predict ahead of time. So this is the problem. But that's why here in especially in Yogyakarta, the district health office and provincial health office try to actively, they try to do active surveillance to look at the hospital reports before they are being sent to the district health office or provincial health office. Because we know that the early warning system is very important, then we can, prepare for the clinical team and the clinical supervision in the hospital. And Dr. Ida is our expert here in this province, for clinical audit sometimes, death conference sometimes, and then we have to learn a lot about clinical management of dengue, hemorrhagic fever, especially in this area. Until now, we still have a lot of morbidity due to dengue and also several mortalities of dengue infection. There are two efforts related to climate change, mitigation to climate change and adaptation to climate change. I think mitigation to climate change, if we want to influence the governments and the communities, we have to put forth the co-benefits of doing mitigation efforts. That if we improve our land use management, and then less solid waste, as potential breeding places of Aedes aegypti, and then at the same time we will reduce emission, CO2 emission or greenhouse gas emission. Then at the same time we will have co-benefit of decreasing the potential of increasing incidence of dengue hemorrhagic fever or dengue fever. And recycling and reuse of materials, because there are containers outside the houses, and then we will reduce the energy consumption for production of the products made from the materials. We try to recycle, and in this case we will reduce emission, and at the same time we will decrease the solid waste as potential breeding places for Aedes aegypti. And this is what we are collaborating with Umeå University, where telemedicine, telebusiness, in which we try to do less travel, less emission, and maybe also less transmission of transportation of mosquitoes to areas previously not endemic for dengue transmission. So these are mitigation efforts with co-benefits for dengue prevention. And the other one is adaptation. Of course, there are a lot of other ideas. Adaptation to climate change. I think we try to efficient use of water, treated water, wastewater to recharge aquifer. Then we will improve better water storage to eliminate mosquito larvae. At the same time, we will adapt to climate change, especially in the times of drought. We also prevent drought. And in this city, there was a proposal to not to store water in the house, but to use showers. But the idea is not well accepted in the city, because maybe, I don't know, somehow it's too expensive or it's not impractical to many people here. And also, if we carry out improved surveillance and response to climate change or climate-related events, because we already experience climate-related events such as storms, shifting rainy seasons, for example, and of course we have flood, we have landslides, and so the government set up a surveillance system for climate-related events, and at the same time we will also be able to integrate a surveillance system to related, not just climate-related events, but also to detect dengue outbreaks. And in fact, we have done that through syndromic surveillance, the system called eWars, early warning system. And I think it's useful, it works in some places, but then it's not well maintained in other places. But I think it is still possible to be reinvigorated, the surveillance system. So we will have integrated system for responding to climate-related events, at the same time also to respond, to prevent, to anticipate dengue outbreaks. Thank you.
Yeah, thank you, Professor Hari. So now we have a few minutes for discussions. Are there any questions? Yes, silakan. Okay.
Thank you very much for the opportunity. I would like to ask Mr. Osa, right? It is very interesting approachment for dengue surveillance using remote sensing. Only from the sensor of remote sensing, we can predict area that has the high case of dengue. But from the in the last picture, you saw that the area of high case dengue is same with you compare with the land mapping using remote sensing, and then I would like to ask how the accuracy from this application, I mean that what the percentage of similarity from the area of high case dengue with land mapping using remote sensing. Thank you very much.